video in this Integrated Math 1 video series. In this video, we're going to focus on something called average rate of change. Before we do that, let's go ahead and hop into our warm-up for today, which has these 5 problems. So go ahead and take a second and do that. Okay, so in number 1 here, we have a question: which function has the greatest y-intercept? If you remember from our previous videos, we've talked about the y-intercept being that constant, that initial value, the value that doesn't change based on x. And so the y-intercept is, I'm going to circle them here, 7 in this first one, 12 in this one, and negative 5 in this one. And so which one is the greatest? Of course, the middle one there with a y-intercept of 12. So the y-intercept would be 0, 12 would be the point for that one there. Number 2, what is 17% of 30? Again, multiply the two numbers involved, 17 and 3, without the trailing 0. 17 times 3, let's see, 10 times 3 is 30. 7 times 3 is 21. 30 plus 21 is 51. So it's some version of 51. It's either 51 or 5.1 or 0.51 or something like that. So let's try to make sense of this. Let's see, 51 is above 30, so it can't be that one because we're taking 17% of 30, so it should be less than 30. So it's not 51, how about 5.1? Does that make sense there? Let's see, 20% of 30, 2 times 3 would be 6, so 20% of 30 would be 6. So it makes sense that 17% would be just a little bit below that, so 5.1. All right, number 3. Simplify 7/3 times 9 plus 4. And so let's see, as we talked about before, we can actually divide by 3 first. So 9 divided by 3 is 3. 9 divided by 3 is 3. Or 3 over 1 if you want to think about it that way. Either way, it's fine. 7 times 3, of course, is 21. So 7/3 times 9 is 21. Plus the 4 is 25. All right, and then up next, graph y equals 3/4 x minus 1. I'm going to just draw a rough sketch here real quick. Okay, so negative 1, as we said a minute ago, is the y-intercept. So negative 1, let's go down 1 right there. It's going to be our y-intercept. And then the slope here is 3/4. So if we put in 4 right here, the 4 divided by 4 is just going to be 1, and so it's just going to result in 3. So if I put in 4, if I go over 4, I'm going to go up 3 there. So if I put in 4 here, it's going to give us 3. So if I go over 4, 1, 2, 3, 4, I'm going to go up from there, 1, 2, 3. So I've got my 2 points right now, and now I can connect them to form a straight line. Any linear function is only defined by, you only need 2 points. And so we can just connect these here, and we can get our line, I'll make it in black here, going through those 2 points. And I'll put the arrows there to signify that they extend on forever in both directions there. Okay, so this is the y-intercept, negative 1, and then the slope is 3/4. So rise over run, up 3 over 4. Okay, or you can think about, putting in multiples of 4 here. If I put in 4, it would reduce to just giving us 3. If I put in 8, 8 divided by 4 is 2. So 2 times 3 would be 6. So I could go over 8, up 6. Really, you can, think about multiplying this fraction by the same number on the numerator and denominator, so creating these equivalent fractions. So 3/4 is equivalent to 6/8, is equivalent to 9/12, and so on. So I could go over 12 up 9, or whatever. So you may have heard rise over run. That's what this signifies here, rise over run. And because it's positive, we're going to be increasing, and so it goes up as we go to the right. If it was a negative slope, it would go down as we go to the right. So we'd go over 3 and down 4 if that was the case. Over 4 down 3 if that was the case. What is the area enclosed by the function negative 4x plus 24? So let's create a rough sketch here of that. Okay, so we have this graph here. Negative 4x plus 24. So that means our y-intercept is way up here at 24. And it's a negative slope, so it's going to be decreasing over time here. As x increases, it's going to be decreasing like this. And at some point, it's going to hit the x-axis. And it's going to create a triangle with the x and y axes. So let's find out what our x-intercept is. We can either go down 4 over 1 every time, down 4 over 1, down 4 over 1, or we can just set y equals 0. When is y 0? What value of x makes y 0? So we can subtract 24, or we can just kind of think about it. We need this to be negative 24, right, to counteract with this 24. So a 6 would work there, right? So we can plot that here at 6. So this is going to be at 6. And so we have this line now. It's being created. So that is our function there. And we want to think about the area that's enclosed by the function, the y-axis, and the x-axis. So it's creating that triangle there. And if you remember, the area of the triangle is 1/2 the enclosed rectangle around it. And so what I mean by that is if we create this rectangle here, create this rectangle right here. It's not perfect, but you get the point here. If we create this rectangle, it's always going to be half of that. So the formula is 1/2 based on its height, but you can visually think about it as 1/2 the rectangle that goes around it there. And so it's 1/2, so the area is 1/2. The rectangle will be a width of 6 and a height here of 24. 6 times 24. So this is the area of the rectangle, and then of course we want half of that. And so we do this a number of different ways. I'm trying to think what would be best for mental math here. So I can do, let's see, if I can use this half any way I want. I can either half the 6 first, or I can half the 24 first. Either way, I think it'd be easier for me to half maybe the 6 first. So we get 3 times 24. So we can do 3 times 20 is 60. 3 times 4 is 12. 60 plus 12 is 72. Units squared, since we're talking about area there. So we don't really know if it's feet or something like that, so I'm just going to put units squared. Okay, so I know that last one was a challenge, but hopefully we can kind of think through this, and maybe next time we're asked a question like that, we might be able to figure it out. Okay. Let's move on to our goal for today, which is to understand how to calculate average rate of change, but also how to interpret average rate of change in the context of a real world scenario. And so those are our goals for today. So to embark on this task, I've got a situation that I want you to think about. So I know you may not be able to read the words, it may be too small, but let me read it for you. So it says, you're a marine biologist working for an environmental protection agency. You are concerned that the rare coral mathmafish population, yes, they said mathmafish, is being threatened by an invasive species known as the fluted dropout shark. The fluted dropout shark is known for decimating whole schools of fish. Using a catch and tag release method, you collected the following population data over the last year as the intervention plan was being implemented. So we have the months across the top. So the initial population was 480, and then of course from there it changes. But throughout this intervention, the EPA was able to reduce the fluted dropout shark population and show the decimation of the mathfish population. Your boss asks you to summarize the effects of EPA's intervention plan in order to validate funding for your project. So they talk about reducing the fluted dropout shark population, but what we have here is actually the mathfish population, which we don't want to increase, right? We're reducing the shark population so that this one does not decrease. So it says graph the data on the following coordinate plane and use the graph to complete the summary report. So maybe what might be best is to jot down these numbers real quick and then I'm going to show you the chart that you can plot it on here in just a second. Okay, so if you see the chart here, we have the Mathma fish population along the y-axis here, and the number of months since first observation along the x-axis there. So go ahead and take a second and see if you can plot those data points on this graph. All right, so once you've plotted these, it should look something like this. So, I've actually written the data values there just so I can reference them in the video, but hopefully your graph looks something about like that. And so we want to analyze this data and figure out some answers to these questions down here. So the first one is calculate the average rate of change of the Mathfish population over specific intervals. Indicate how and why you chose the intervals you chose. So I know you may not know exactly what average rate of change means yet, but see if you can kind of figure out different things to calculate about this graph. So see if you can kind of figure out what this is meaning by calculating the average rate of change of the Mathfish population over specific intervals. Okay, so there's actually a lot of different intervals you can choose here. In fact, there are 78 different pairs of points that you can calculate the average rate of change with over the course of these 12, actually 13 if you count 0, 13 months. So we can just pick a few and we can kind of work through this together. So how about we analyze the average rate of change from, let's say, month 2 to month 3. So from month 2 to month 3, the population of Mathfish go down. And so we can figure out maybe what the average rate of change in between those two values is, because it didn't just all of a sudden at the end of the month just all of a sudden decrease, but we can think about over the entire month, how did the Mathfish population change? And so what we can do here is we can take the change in population, so that would be 417 minus 318 divided by the change in month. And so you can go from 2 to 3. So if you subtract here, we're going to get 99, negative 99, let's see, over negative 1. In fact, it's positive 99 over negative 1. So it'll be negative 99. So really it's the slope. It's the slope between the 2 points. So the average rate of change between months 2 and 3 is negative 99 Mathma fish. I'm just going to say fish per month is the current rate of change at that interval between 2 and 3. Okay, but there's other ones we can do. We don't have to go from consecutive months. We could go from let's go from month. I'm just going to erase that real quick. Let's go from month 4 to month 12. And what is the average rate of change there? So from month 4 to month 12, and you don't have to do it in the same order as we did in the last one. You can do 46 minus 240, so it's the difference in the population divided by the difference in months. Just make sure you start with the same months that they correspond to the values you did up here. So if we start with 46 up here, we're going to start with month 12 down here. So 12 minus, 240 corresponded to month 4, so it'll be 4 there. Okay? So 46 minus 240 is negative 194. Divided by 8. Gives us a negative 24.25 fish per month. So we're losing, on average, we're losing 24.25 fish per month over this interval from 4 to 12 months. And so if you compare them, is it getting better or worse? Well, this interval here, we're on average losing 99 per month. And then here, on average, we're losing 24.25 per month. It's getting better, right? Over those, if we compare those two intervals. But you could compare a lot of different things here. Like I said, there's 78 different ones you could analyze to come up with, because it just said choose some intervals. So maybe you chose certain intervals because you thought maybe it was the steepest decline, or maybe you thought it was the most increase of population. Whatever it is, whatever the reason is, hopefully you stated that, but there are a lot of different ones that you can compare here. So our next question is, over which interval was the population decreasing the fastest? Decreasing the fastest. So we can kind of think through that a little bit, and maybe we can do that by looking at a couple different things here. One is, I've written down the amount of fish that it changed each month. So we went down 8 the first month, 55, 99, 78, 88, 49, 19, 37, 15, 8, and then we started going up. We went up 5 and then up 17 to finish it off. So over which interval was the population decreasing the fastest? And so in a 2-month span, or from 1 month to another one, the fastest decrease was here at 99. So from here to here, we lost 99 fish over that month, and that was over consecutive months. The most of it decreased. Now there may be another interval that is more of an increase, and we're going to check out this maybe graph here where we've connected all the dots. We can just examine their slopes. So the slopes between any 2 points, I don't think would be more than that. Let's see. This one right here is pretty steep, right? But is there one that's maybe steeper, or maybe one that we could connect that's steeper? Like if we go from here to here, is that as steep of a decrease? It's not, right? It's not as negative of a slope there. And we could analyze a lot of different things here. Of course, from here to here, it's not as negative. What about from 7 to 8? What that one was from 7 to 8. It was negative 37. So quite a bit there, but not nearly as much. And so from months 2 to 3 is the interval in which the population is decreasing the fastest. During what month did you notice the largest effects of the EPA intervention? So it's kind of a loaded question, because you might say that it's when we start increasing in our population, but that was not a huge change. Like it only went up 5, for example, there, and so we might look at how these are changing and where's the biggest change in the change in the difference between the two consecutive months, and so from here to here, for example, we are negative 10 there, right? It actually got worse from this month to this month. But what about this next one? This next one, it goes down not quite 40, but maybe like 39. So it actually got better by 39, because we didn't lose 88. We only lost 49. And so that's an improvement, right? Because we improved in the number that we were losing. And then in the next one, it's actually a plus 30 there. So it's continuing to get better, but I think it's in this time span that we're really starting to see the difference of this intervention, because it starts to decrease in terms of the number that we're losing each month. Now, it got a little bit worse here, minus 37, so it kind of got worse there, but then we started to see some of that, curving upward effect of the treatment. So I think we start to see the impact in here, but we hopefully start to see some of the increase in the population starting at month 11, 12, and so on. So however you reason through it, however you justified your answer for that one, I'm sure it is fine. Number 4, explain the overall effects of the intervention. We kind of just did that, talking through how this impacts the population. But most important thing here is understanding the average rate of change, and that we can calculate average rate of change by calculating the change in population divided by the change in time. And really that's how we can generalize it. It's the change in quantity divided by the change in time. Average rate of change will always be with respect to time. And so in this case, it was fish per month. It was the rate that we were describing. But in a new case, we've got distance from the start of the road. So we're talking about the two things traveling along the road. One is a bike and one is a truck. We're talking about them traveling along this road here, and it's in terms of time in seconds. And so we can think about how the distance, which is our quantity, changes with respect to time. So if you notice, the bike travels at a steady rate. The bike travels at a steady rate, and what that means is it's a linear function. So it's got a constant rate at which it's traveling here for the bike. Whereas the truck, in this scenario, travels at this path here. And so a couple things we can do here. One is we can calculate the average rate of change of the bike. Another one is we can calculate the average rate of change of the truck, and we can compare them. So in this scenario, let's take the average rate of change of the truck from about 8 seconds, so here, to about 10.5 seconds right there. So let's think about that for a second. What is the average rate of change of the truck in this scenario? Well, what was the distance? The change in distance. Change in distance was about, 130 to 165. So about 35. It would increase about 35. Whereas we went over about 2.5. So the change in distance, or the change in quantity, was 35, and we got that by doing 165 minus 130 approximately. We don't have values for these necessarily, but approximately 130 divided by the change in time, which was 10.5 minus 8. So that's 35 divided by 2.5. So 35 divided by 2.5 is 14. So 14, it's in feet, so feet per second is what we're talking about here. So even though the truck continued to move away from the start of the road, and then it kind of flattened out, so basically the truck is stopped at this point. The truck is stopped. The time is going on, but the distance away from the start of the road, it's not changing. So the truck is stopped at that moment, maybe at a stop sign or a red light or something like that, and then it picks up and it continues on. But the average rate of change of the truck over that interval is 14 feet per second. But think about if we were to calculate the average rate of change of the bike over that time. It would still be the same, right? Because they share these endpoints of the interval. So the change in distance over change in time would actually be exactly the same for the bike. And in fact, wherever the bike and truck intersect, over those intervals, they will have the same average rate of change. So from 10.5 seconds to 17 seconds, they will have the same average rate of change. In fact, it will still be 14 feet per second because the bike is always 14 feet per second in this instance. And so this is kind of an interesting way to calculate. Let's just do one more example, and I'll give you a chance to try one real quick. I'll give you some values to work with and see if you can calculate it. So let's go from 0 to 8 seconds. So 0 is going to be 0 feet at 0 seconds. And then here it's 8, comma, we'll say 130. And I want you to compare it to the bike. So the bike here is got a little head start. So it's at 0 seconds, it's at 10 feet. And it goes to the same point there. So I want you to calculate the average rate of change of the truck from 0 to 8 seconds and the average rate of change of the bike from 0 to 8 seconds and see what you get. Okay, so let's do the truck first. So the truck would be 130, so change in distance, so minus 0, divided by the change in time, which would be 8 minus 0. So it would be 130 divided by 8, which is 16.25. 16.25 feet per second. So right away we think, or at least we conjecture, that that's greater than the bike, because we thought the bike was 14 feet per second. Let's calculate it though. All right, for the bike we have 130. Do this in red instead. 130 minus, so we're talking about the change in distance here away from the road. So 130 minus 10 would be 120. And the change in time, again, is 8. 8 minus 0. So we get 120 divided by 8. And 120 divided by 8 is 15. So these numbers I made up maybe are a little bit off. So maybe that's not. Maybe that's why the difference between 15 and 14, as we saw in the last one, because we just kind of guessed what this value was here. So that may be the reason why we're off a little bit. But yeah, the average rate of change of the bike is 15 feet per second. Either way, the truck has a greater average rate of change over that interval, and here's why. They traveled, it's the same time, right? So it's still 8 seconds no matter what. The truck traveled further over those 8 seconds. Let me say it again. The truck traveled further over those 8 seconds. So of course it should have a greater average rate of change. Or really, what are we talking about here? We're talking about speed, right? In feet per second, that's speed. So hopefully that gives you an idea there. All right. So another scenario I want to give to you, and we'll finish up here, is a real life example of average rate of change. Years ago, police, they did not have the sensors, the radar guns that could track how fast you're traveling as a car. So what they would do is they put a chalk line in the road over here, and they put a chalk line in a road over here, and they would know the distance in between those two chalk lines. And what they would do is they would sit there with a stopwatch, and they would calculate how long it took you to get from point A to point B. And regardless of how fast you were going in between the two chalk lines, it didn't matter. All they could calculate is the average rate of change or average speed in between those two chalk lines. And so it's interesting to think like toll booths. If you travel from one toll booth to another toll booth, and they know what time you started and ended, they could actually give you a ticket for speeding if your average speed is over the speed limit. Because if your average speed was 65 miles per hour, for example, at some point you had to travel 65 miles per hour or over 65 miles per hour if it was over 65. And so anyways, hopefully that kind of gives you an example of, you may have traveled all kinds of different speeds in between the two chalk lines, but we can calculate the average speed in between those two, and that's called average rate of change. All right, so hopefully that kind of gives you a good idea of average rate of change, not only how to calculate it, but how it works with the context of the situation and in the real world in terms of the bike and truck, but also the math and fish task. All right, so that's it for this video. We'll see you next time.